Okay, good afternoon, everyone. Let's continue the discussion about Zener diodes. So first, I want to bring up just do a quick recap of the introduction. Let's make sure I'm in the right section. Section 224. Okay, so Zener diodes. Zener diodes are like regular diodes, except they are specially or specifically formulated to operate in the reverse bias. Okay, so in the forward bias, Zener diodes behave like a regular normal diode made out of silicon. It'll take 0.6 to 0.7 volts for it to conduct in forward bias, exactly the same diode characteristic. In reverse bias, if you take any normal diode and you apply a reverse voltage, right, would not see any current. If you keep on increasing the voltage, the electric field density keeps on increasing. And at some point, minority carriers are ripped out of their lattice structure. Large number comes free, and then avalanche and impact ionization effects occur, and then you have a large current flowing in the reverse bias. This is known as the breakdown, right? The voltage that is required to accomplish this is known as the breakdown voltage. In a regular diode, regular silicon diode, that voltage could be in tens of hundreds of volts. Like the standard 1N4000 series, the regular inexpensive diodes that we can buy off the shelf can go up to like 400 volts in reverse bias without breaking down, okay? But Zener diodes are specifically formulated, meaning the design, the geometric design, as well as the doping profile both contribute to a far lower breakdown voltage. Okay, so in brief, I had covered two effects. One is the Zener effect, the other one was the avalanche effect, right? Zener effect occurs for voltages less than 5.6 volts. Avalanche effect occurs for voltages greater than 5.6 volts. But in general, all Zener diodes, all diodes that operate in reverse bias, whether they are due to Zener effect or due to avalanche effect, are all referred to as Zener diodes. Again, there are two separate mechanisms, but all diodes operating in reverse bias are known as Zener diodes. So, geometric design, very, very thin junction, and doping profile, heavy doping profile. So you have extra charge carriers than in a normal diode present in a Zener diode. So the breakdown occurs at far lower voltages. We can get Zener diodes breaking down from like 2 volts all the way up to like tens of hundreds of volts. Okay. Typically, the normal Zener diodes that we use in the lab and electronic circuits would be in the range of 15 to 20 volts. Okay. But starting from 2 or 3 volts, going up to 15, 20 volts. So in forward branch, it behaves like a regular diode. In the reverse branch, when it breaks down, the specific property is any diode that breaks down, a huge amount of current starts flowing. It saturates at a level. Sorry, not saturates level. It keeps on increasing, and the voltage remains near constant. Okay, the voltage remains near constant. So if you look at the characteristic of any diode, forward bias, you have the standard diode characteristic. Reverse bias, you have this breakdown. This breakdown voltage for a normal diode is very large. Okay, normal diode breakdown voltages typically exceed hundreds of volts. Okay, hundreds of volts. Even the cheapest silicon diode that we use, 1N4001, 1N914 can handle up to like 50 volts. Okay. In a Zener diode, VZ is referred to as the breakdown, the breakdown voltage is referred to as VZ, the Zener voltage. And VZ can range from 2 volts to hundreds of volts. Okay, so the breakdown occurs far earlier than far earlier than in a normal diode. Okay, again, because of the heavy doping profile. All right, so what happens at breakdown? We can see that it conducts in both forward bias and reverse bias. So the only difference between a Zener diode and a regular diode is that the breakdown is controlled and it occurs far earlier. Okay, so it conducts both in the forward bias as well as the reverse bias. But the difference is in the forward bias, no matter what kind of design we create, no matter what kind of doping profile we use, the forward breakdown will be 0.6 to 0.7 volts. That is the material property, right? It's one of the curious things about semiconductors. In the reverse bias, though, we can actually control the breakdown voltage. And that's the key thing. We can control the level at which the junction will break down. And once it breaks down, a diode will hold the voltage across itself constant. So again, whether it's a regular diode or whether it's a Zener diode, the voltage is held near constant. Even the slight slope that you see here at the curve at the beginning of breakdown, even that is exaggerated. Like we have performed, we perform experiments using Zener diodes in other lab classes, and we use like 5.7 or 6 volt Zener diodes, and there's barely any difference between the breakdown and then once it crosses the breakdown. So barely like millivolts difference, but the current increases by large amounts. Okay, so the current increases by large amounts. And so again, this is quite large. Large amount of current starts flowing through the diode itself in breakdown. So if current increases and the voltage remains near constant, then we can represent or model that Zener diode as a constant voltage source because it is providing a constant voltage at the output. And hence the model in the reverse branch is a constant voltage source. Okay, constant voltage source. So in the forward bias, it's like any of the regular diode. In the reverse bias, it acts like a constant voltage source. It is supplying a constant voltage, and that voltage would be known as the Zener voltage. All right. Okay, any questions thus far? So far, so good. Okay. All right. Let's talk about the notations. All right. Standard diode symbol, except a Zener diode has whiskers on the cathode. That's the cathode. That's the anode. Diode voltage, VD, is always measured with positive reference at the anode, negative at the cathode. Current flow is always indicated as flowing from anode to cathode. That's ID. Okay. That's normal. That's normal diode convention. If we say diode voltage, anode is positive, cathode is negative. If you say our diode current ID, it's always flowing from in the direction of anode to the cathode. That's standard. However, the Zener diode is always operated in reverse bias. Well, you can use it in forward bias too, but then there's no sense in using that. So Zener diode is always operated in the reverse bias, and because it's operated in the reverse bias, current is always flowing from cathode to anode, and voltage is always measured with the positive reference at the cathode. So VZ is the opposite of VD, and IZ, the current, again, because it's flowing in the opposite direction, it's going from cathode to anode, positive reference is at the cathode. For almost all circuits, if you see a Zener diode, we simply refer to VZ and IZ. We never refer to VD and ID when it comes to a Zener diode. Okay. So keep the conventions in mind. And again, because it's flowing in the opposite direction. Uh, just a second, let's see. All right, so current increases and it remains large. So how do we use it? Okay, how do we use it? All right, so let's take a simple circuit. Let's keep this on the side. Let's stick a pin in it for a minute. Let's take an idealized circuit. This idealized circuit has nothing except a Zener diode. That's it, nothing else. Okay, plus minus V in plus minus V out. And of course, plus minus VZ. Everything's in parallel. All right. V in coming from the left, V out being collected at the right. All right. Now, let's assume a voltage VZ of 5 volts. Okay. The Zener diode is designed to break down at a voltage of 5 volts. So VZ is 5. Now, if V in is less than 5 volts, V in, the input voltage is less than 5 volts. Is the diode on or off? Regular diode, connect in reverse bias. What happens to the diode? What current do you expect to see at the output? Zero current. So in reverse bias, unless and until a diode breaks down, current is almost zero. Same thing for Zener diode. The only difference between a Zener and a regular diode is that the breakdown voltage is designed and controlled. There's no other difference. So if the voltage is less than the breakdown voltage, meaning the input voltage applied to the Zener is less than the Zener voltage, diode remains off. It's reverse bias, no current flows through, except for the small saturation current. So let's just say, because this is an ideal circuit, let's just say D is completely off. The diode is off. But now you slowly start increasing the voltage, and some point V in crosses 5 volts, and diode D is on. And obviously, this is an ideal circuit, not possible in real life. So we are saying even if the input is equal to 5 volts, diode turns on. In real life, there are plenty of other considerations. Okay. So once the diode turns on, what happens? The reverse current starts flowing through. Junction is broken down. Current starts increasing through the diode. Okay. But it holds the voltage across itself constant. Holds the voltage constant. So IZ that is flowing through in this direction increases. So as V in increases, I in input current also increases. Therefore, IZ increases, but VZ remains constant. Okay, VZ remains constant, which makes sense by all laws of physics and Ohm's law. If you increase the voltage that you're sending in, you're also increasing the current, meaning you're increasing the power that is being sent into your circuit. Now, at the receiving end, meaning the Zener diode is receiving that increase in power, the voltage remains constant. P equals VI. P increases, voltage remains constant. That means I must increase, which is what happens. Zener diode sinks a lot of current. So a large amount of current flows through the Zener diode, and Zener diode provides a pathway for that increased current to flow through. And because the Zener diode is providing a pathway for the current to flow through, it is known as a current sink. A current sink. And this is true not just of Zener diode, but it's also true of any device. I believe we used one of the procedures in one of the labs. I can't remember exactly which one, but we used the transistor as a current sink. That device, any device that provides a pathway for current to flow through, is known as a current sink. If it's supplying, then it's a current source. But if it's allowing a pathway for the current to flow through itself, then it's a current sink. So Zener diode current increases, but the voltage remains constant. Okay, I saw you first, so you first. So the question being asked is, if a microcontroller board has a 5 volt and a 3.3 volt output, for instance, like an Arduino perhaps, is the voltage regulated by a Zener? That's a good question. The answer is I actually do not know. But if I had to guess, I would say yes. Zener is perhaps the most rudimentary and the easiest way to provide voltage regulation. But there are off-the-shelf regulator components we can buy, and those are also very cheap. So yes, it's quite a possibility. I think you have piqued my interest, so I'm going to go look it up right as soon as I'm done with my classes today. What kind of Zener diode it uses? I mean, what kind of regulator it uses? Yes. So it acts like a sink relative to V out. So if I'm understanding you correctly, the question being asked is, if the Zener diode is allowing the current to go through, what is going to V out then? Right? So again, it's a good question, but right now it's just an idealized circuit. But I'm going to add in resistors, which is the circuit on the left, and then we'll talk about the rest of it. Yes, that's coming up next. Yes, all good questions. That means all of you are thinking. All right, other questions? Okay. Let's see. How much time? 2:55, 4 minutes left. Okay, so that was an idealized version, right? So one of the important questions being asked was, if we are increasing the current from the input and the Zener diode is taking everything, what is going to the output? Well, that's where the resistors come in. Now, the Zener diode has two ratings, two most important and fundamental ratings. One is the Zener voltage. The other one is the Zener power, PZ. PZ is the maximum power the Zener diode can handle. Okay, so again, as I stated, VZ remains constant, right? VZ remains constant, and it can sink a lot of current through it. But there is a limit to how much current it can handle. If that current exceeds a certain limit, then the power that it can handle has a certain limit, right? Beyond that, there's so much extra heat generated, Zener diode is going to blow up. So two important specifications, VZ voltage and PZ power. Now let's come to this circuit. For now, let's say we have a voltage source, input on the left, we have a resistor, and now we have the load. Okay, this load is R. This is a current limiting resistor known as RS. What kind of circuit do RS and R form? Okay, this is VS, so let's do supply voltage VS. Two resistors in series, you apply a voltage to it. What happens to the voltage? What happens to the current in a series circuit? I'm going to talk to your 115 professor and get your grades back. It remains the same. Series circuit current remains the same. There's only one road around the block. If you start driving from voltage Vs, you only have one road to go around the block. Current remains the same. However, voltage gets divided. So it's a voltage divider circuit. A parallel circuit of resistors is a current divider circuit. Series connection of resistors is a voltage divider circuit. So because this is a voltage divider circuit, voltage gets divided across Rs and R in proportion to the value of the resistors, right? It's a voltage divider circuit. In Rs and R will have certain voltage. Now, because it's a voltage divider circuit, let's say Vs is 10 volts. Okay, 10 volts. And if Rs is 100 ohms and R is equal to 900 ohms, what is VR? Voltage across that resistor R. Again, nice round numbers. 10 volts applied to 1000. 1:9 ratio. 9 volts. 9 volts. Okay. 9 volts. And VRS is 1 volt. Okay. Now, if we connect a Zener diode right here, you have 9 volts available that is being applied to that Zener diode because of the voltage divider circuit. Okay. The reason I'm explaining this way is because without the Zener, it makes sense. With the Zener, if you put it in there, then it doesn't seem as if it's a voltage divider, but it is working and functioning as a voltage divider circuit. So the point here is if your Zener diode VZ is 5 volts, then the voltage applied to that Zener diode is 9 volts. So what happens to that Zener diode? Does it turn on or does it remain off? V in is being sent in 10 volts. 1 volt drops across Rs. So the Zener and the load resistor R see 9 volts across their terminals. Zener diode is rated for 5 volts. Does it turn on? Yes, it turns on. If a diode D is on. Now, if Rs goes to 900 ohms, R is 900. What is VR? 5 volts. Just divided exactly in half. It's 3 o'clock, so if you have to leave, you can leave. Let's say it's an ideal circuit. We'll say that diode is still on. Okay. But now let's say your load changes. Instead of 900 ohms, now your load drops to 500. Oh, 500 ohms. What happens to VR now? Now VR is far less than 5 volts. Your diode is not going to turn on. Okay, diode is not going to turn on. The important takeaway from this is that there is a limit on the kind of load that you can connect to the output. If it's just a simple Zener diode, the circuit must be designed in a way that you have a range of load resistances or loads that you can connect to the output of that circuit. Otherwise, it would not work. Okay. There's also range limits on the series resistance RS, but we're out of time. So we're going to stop here today and we'll pick up here again on Wednesday. And then I'll look up the answer to what voltage regulation is used. Let's ask ChatGPT. We have free access from today, right? So let's see. Let's see what ChatGPT says. Yes. Okay. All right. Let me, I can, you're ready to upload now? Wait. For the quiz. It didn't submit. So you send it to, you send me the email, right? Let me open it up.
But you could do that. I actually want to know.
Okay, so let's do this. Nah, not useful. I mean, obviously, this is just a starting point. So we don't, it can only access the public resources that it has available, but we can use it as a learning tool, not as a crutch.
I have no idea.
Which one? It's a voltage regulator, but it's not a Zener diode. Okay. LM7805. Yeah, that's the off-the-shelf regulator that we use. Okay. All right. Let me stop the recording for now, and then I can answer your questions.